Okay, Assalamualaikum. Good evening. So, one of your friends actually asked about support reactions, right? Regarding for 3D cases. Okay. So, we're going to talk about a special case actually, that your friend has highlighted. Okay, let me draw an example. So, let's say, for example, you have a pipe, okay? You draw a pipe, okay? Oops, so a triangle. Oops, my bad, yeah? So, we're going to be a pipe, okay? And we're gonna draw some journal bearings on it, okay? So we're gonna draw some journal bearings. Okay, so we're gonna have a journal bearing here, one more journal bearing there, and the last one right here, okay? So we have a journal bearing, alright. Oops, sorry, that's not how I'm supposed to draw it. And we call them A, B, and C. Okay, so one thing that we should be aware about journal bearings is that journal bearings actually resist, right? They resist both force and couple moment, okay? They resist both force and couple moment. Oh, by the way, before I want to mention, let's just add a force here about, let's make it orange. I'm going to put a force that's going to go in this direction, about maybe let's say force of F, okay? So they resist both force and couple moment, okay? And normally, in special cases where we would have the journal bearing perfectly aligned, okay? So let's say, for example, we have perfectly aligned, then we don't consider the moments. We do not consider the support moment reaction. Moment reaction. Okay, so what I mean to say is that let's say we draw the free body diagram of the example above, okay, with their respective axis, okay, X, Y, and Z. And I'm gonna use a purple color, by the way, just to draw the thing so it'll be easier to visualize. Okay, right. And for the journal bearing A, we have the support reaction force here, that is AZ, and of course AX, right? For journal bearing B, same thing. We also have here, let me just draw up here if you don't mind. Yeah, it's the same thing. We also have here BZ, okay, and BX, right? It cannot move. And then for journal bearing C, we cannot have here CY and CZ, right? And let me see, we also have the force F, right, which is obviously going to be here, right? Yeah, force F in this case. All right, so force F. Anything else I'm missing? Maybe. Okay, maybe you can also add another force here as well, just to make it a bit more clearer. So sorry, be like a force, like let's say, let's see what force we can give here. Let me give a different color, yeah? Call it here another F. Or we call this another force B. Not B. Let's call it G. We call this force G. Alright? So we also have a force G also in the Y direction. Okay. Alright. So with that being said, if we know the forces F and G, the forces F and G are known. So how many unknowns we're left with actually? Is that we're left with 1, 2, 3, 4, 5, 6. We have 6 unknowns, right? And the thing is, our equation, our free body diagram equation actually for 3-dimensional objects, we're only limited with this 6 equations. So summation of fx is 0, summation of fy is 0, summation of fz is 0, okay? And summation of mx is 0, summation of my is 0, and summation of mz is 0. So we are left with 6 equations and 6 unknowns. So 6 equations, okay, and 6 unknowns. So this problem is solvable. We can actually solve the problem. So can be solved. Right? And we don't consider moment also actually. That's the reason being, let's say for example I take a point here. I call this point D, okay? We call this point D. Okay. So if you see from point D, alright, what really happens here is, let's say we take from point D to BZ for instance, okay, for example BZ. Right, so let me draw like a position vector here. So let's go to BZ. So what's gonna happen, right? So from BZ, we're gonna actually end up with having what? We're gonna end up having a moment in the x direction, right? We're gonna have a moment vector that is going to the x direction, for instance, okay? And if you find another vector right here, that would be AZ in this case, right? AZ, okay? So if you draw AZ, then you also have a moment vector in the x direction as well, right? You also have a moment vector that would end up going the x direction, but this will tend to counter it, by the way, okay? So this will act like a, okay, it's a red color actually. I think let me just draw in red to be easier. So this one will act more like a counter, okay? So this vector right here will go as a counter. So these two, right, they'll tend to cancel out, okay? So that means xc is equivalent to x, right? To negative x, okay? So meaning to say that these two vectors will cancel out. And if you were to also do for point D, right, if you were to take point D and take it for other support reactions also, eventually you'll find that they'll all have a counter to each other, even also with respect to F and G, where F is actually basically, if I were to highlight it here, F is basically in the Z direction, right? It's going Z, and G is basically, sorry, let me use a bit more brown color. G is basically in the Y direction, right? Eventually you'll find a counter that will cancel all of it out. So therefore, that's why we don't consider the typical moment support reactions normally associated with general brackets. For example, we do not consider the MAX. Okay, we don't really consider MAX because it's all being countered by the other support reactions. If you take a moment at a point D itself, we're gonna find out that eventually all the support reactions will generate moments that'll cancel each other out. Therefore, there is really no need for us to find the MAX, MAZ, okay? Same also goes to here, so MBX, right? And then MBZ, sorry, MBX, my bad, my apologies here. It's supposed to be Z, yeah? Okay? So we don't really need to find that. And then we have MCY, okay? And MCZ, alright? So we don't really need to find that actually. Okay? That's one reason. The second reason, like I said earlier, we only have 6 equations. We only have 1, 2, 3, 4, 5, 6. And we only have 6 unknowns, which I mentioned earlier, the support reaction forces. Okay? So we can easily solve these 6 unknowns actually by the help of these 6 equations that we have here. If I were to introduce the moment reactions, right? If we were to introduce the MAX and all that, then we'll have so many unknowns actually. Okay? So I think let me just count from here. Right? So it'll be 1, 2, 3, 4, 5, 6. So we have 6 more unknowns. So let's say for example you have 6 equations and 12 unknowns. We cannot solve the problem. This will become what we call a statically indeterminate. Okay? Indeterminate. Okay? Indeterminate. Determinate. Okay. Alright? Becomes a statically indeterminate problem which you cannot solve. Okay? That's why it's enough just that we have the support reaction forces, right? And we don't really need to consider moment, like I said before, because they'll eventually cancel each other out. So therefore, the object or pipe itself will not move. Alright? So just in conclusion, if we have an object, okay, with, let's say, multiple bearings, right? Whether it's journal or be it truss bearing. It can be journal, truss, bearings, or if we also consider the case with pins or hinges, right? Basically any of the support reactions which counter, basically support that counter both force and moment. Force and moment. M-O-M-E-N-T, moment. Okay, bearings or basically pins or hinges support the counter both force and moment. We don't need to consider the support moment. Okay, support moment if they are perfectly aligned. Okay, they are perfectly aligned. Okay, this is only for this case when they are perfectly aligned actually. And if let's say you're still lost, you don't get the logic behind what I was saying earlier, if you're like a bit confused on why is this the case, you can also try some real life examples. Like look at your door, for instance. Okay, let's say for example you look at your door, right? What's holding your door are obviously two hinges, right? You're holding like two hinges. Okay, so it's called a hinge 1 and hinge 2. Okay, so the hinge 1 and hinge 2 allows you to rotate the door in a certain manner, right? It only allows you to rotate the door in a certain manner, basically where there's no support reaction acting on the door, so that you can open and close the door, right? Because the other, if I were to draw the support reaction, for instance, let's say, let me draw now with the free body diagram. Yeah, it'll be easier to make it easier for you guys to understand. Let's try to do a free body diagram here for the door. Okay. Oops, sorry. Okay, let's pretend it's okay. X, Y, and Z. Okay, and we draw the door. Okay, I'm gonna draw the door right here. Okay, I know, let's use a different color. I think it would be easier if you use red. Okay, let's use red. Okay, so let's say we have a door right here. Okay, parallel to the y-axis. Okay, it's like a solid block. Let's pretend that's your door. It's supported by two hinges. So meaning to say, let's say I have hinge A, so it means to say that we have the force AX, right? It cannot go to the side. And then we also would have, because AX will be clear, we also have AZ, okay? And then also we would have here AY, because it can't move. Likewise, we would have here BX, BZ, and BY. Okay, so the hinges of the door are perfectly aligned, meaning to say like there is no misalignment at all. So no misalignment. Okay, the door is perfectly aligned, right? And then you apply a force F to the door, for instance. So this force F, okay, you apply to the door, and if you, let's say, were to take it from the door's point, the point that you rotate the door, okay, let's say for example we call this point O, and you find the moment, you'll find that the moment is actually only rotating along the z-axis, right? Because the hinge allows rotation along the z-axis, whereas for the y and x, as you're well aware, that you'll create a moment, right? Support reaction moment. So this is MAY, for instance. Okay, MAX, and so on. We also got for MBX, right, and MDY. Okay, because we cannot rotate in the X and Y, but we can rotate in the Z direction, right? That's how you open and close the door. Okay, that's the idea behind it. Actually, it will not rotate along the MAX, not the MAY, MBX, and MBY, because it's perfectly aligned actually. And we don't need to concern ourselves with these moment actually. We don't have to consider ourselves with MAX, MAY, MBX, MBY at all, because quite clearly, yeah, if you were to take the moment at point O, let's say for example, and you were to find, let's say, the moment between O and AX, BY, okay, if you were to find a moment between that, it will counter the force F. Let's say the door is not moving, okay, let's say you're applying the force and the door is in equilibrium, then you'll counter that force actually anyway, right? So sorry, if you, let's say for example, take O, my apologies, yeah, I was a bit confused. Take O and you find a moment at point AX, it will tend to rotate this way, okay, and then for MBX it will tend to rotate this way, so they tend to counter each other, right, at Y. So therefore the moment at Y will automatically become 0, right? So therefore we don't introduce the MAX and MBX actually. We don't need to have this MAX and MBX. Okay, it's redundant because the fact is they will cancel each other out. Alright, when you take a moment at point O respective to AX and respective to BX, you will actually get a moment here that will cancel each other out eventually. Sorry, that's not MAX, my apologies. It's supposed to be for Y, yeah? We were talking about Y earlier, my apologies. So MAY and MBY. Okay? So it will not be redundant actually. I mean, it will be redundant, that's the thing. The point is that this will be redundant. Okay, I put an R here, redundant. Because at the end of the day, the support reactions are more than enough actually to, how do I say, to get the moment, which will obviously cancel and not make the object move because they're perfectly aligned. The supports are perfectly aligned. That's why they ignore the redundant forces. Okay, so hopefully this was clear. I know it's a little bit of a very confusing topic, but actually once you see this work in real life, for example, like your door, or like for example even at your pipe, okay, if you were to go to your pipe, for example, the nearest pipe around your room or mahalla or whatnot, and then you can also try to grab it a little bit and try to shake it, see if you can make it rotate or not. It will technically not rotate actually because it's being held in place by these bearings, right, by these bearings itself, which obviously are perfectly aligned, right? Same with your door as well, okay. You cannot rotate it in the y-axis. You can try to rotate your door in the y-axis and see what happens. Eventually nothing will happen because you couldn't rotate it at all, right? So because it's perfectly aligned, that's why you don't really consider the support moment, okay. And let's say if misaligned, okay, let's say for example if misaligned, let's say for example you have your same pipe here, okay, and let's say we have the general bearings, okay, maybe we have general bearing 1 and then we have general bearing 2, and they're not properly fitted by the engineer. Maybe for example, if I draw a cross section, let's say we draw the cross section of the pipe right here, and the general bearing is maybe not properly fitted. Let's say it's something like this, got a gap. So you see we have this gap here. This is what we call the gap, okay, due to misalignment. Okay, if we draw the cross section of the general bearing, right, so this is a gap here, misalignment. Okay, so what happens if you have a misalignment? So if you have a misalignment, that means that tendency to rotate. Okay, so there's a tendency to rotate, so we need to worry about moment support reaction. Need to worry about moment support reaction. Moment support reaction. Okay, so because there's a tendency to rotate, so you need to worry about the moment support reaction because it's misaligned. But when it's perfectly aligned, okay, when there's no misalignment, then you don't have to worry about support reaction. No need to worry. Don't worry about moment support reaction. Okay. So yeah, for statics, all your cases will be perfectly aligned, meaning to say that there will be no misaligned structures lah in your midterm and your other tests and quizzes and final exam. It'll all be perfectly aligned actually. So this is just the case, yes, with hinges, bearings, or with hinges. Yeah, if you have multiple of them and they're perfectly aligned, which is usually the case, then you don't have to worry about the support reaction moments. You can just simply find the forces, because it's more than enough actually. As I've shown before, the forces also will counter act against the moment, so there'll be no turning effect. All right. And another reason, a very key reason actually, besides this, is that we're only given with 6 equations. Yeah, 6 equations, and we can only find 6 unknowns. We cannot, for example, let's say have 12 unknowns or more than 6 unknowns and try to use 6 equations to solve it. It's quite impossible. It's what we call a statically indeterminate problem. So yeah, hopefully this is clear, and if any questions, please do let me know.